Good morning. Nice to have you here. Because today we want to talk about quantum computers from the cybersecurity perspective. Because typically quantum computers are seen as powerful weapons against classical cryptography. But we don't have to ignore the fact that they could be possible targets as well. So join us to explore various ways in which quantum computers could be attacked and the motivations behind such attacks. My name is Adrian Colesha. I'm an associate professor at Technical University of Cluj-Napoca. I'm also a security researcher at Bitdefender, and here is my colleague Sorin, co-founder of Transylvania Quantum and software engineering at the same company. We are coming from Romania, from Cluj-Napoca, a city in the Transylvania county. Is this a Transylvania where all those stories about Dracula are coming from? Yes, it is. Though that talk is not about Dracula, not even Dracula using quantum computers, maybe attacking quantum computers in some way. Actually, this talk is about the work of researchers from Bitdefender and Transylvania Quantum that analyze the way and the relationship between quantum computers and cybersecurity. In particular, trying to ask the question, how vulnerable are quantum computers? We tried to identify all the possible threat models, all the possible attack vectors regarding on quantum computers. Why? Because, as I've told before, typically quantum computers are understood as weapons to break classical cryptography. We want to take another perspective, which is often ignored, that quantum computers could be possible targets as well. So we try to identify all the possible attack vectors, and also along the way, we try to develop some proof of concept attacks. We investigated some popular quantum software development kits and also work with some popular quantum providers, which fortunately provide free access to their quantum computers. Okay, before delving into details of our investigation, let's see a little bit what quantum computers are, how powerful they are today, and how they could be accessed and used. Because Sorin is our quantum expert, I will pass the floor to him to let him introduce us in the world of quantum computers.
Thank you, Adrian. Hi, everyone. So quantum computers, what are they? Simply put, they are just machines that do math using quantum effects. But why do we need such machines? We already have pretty good classical computers that do math or computation very reliably, very cheap. Why do we need anything else? So we can use our computers to do precise calculations. We can calculate where the moon is going to be 4 years from now. We can start planning a moon mission today. In more complex scenarios like weather patterns, we cannot have precise calculations, but we do simulations, and that gives us a pretty good answer in most cases. In chemistry and molecular physics, we cannot do this. We know the laws of physics, we know the Hamiltonian or a formula that governs the behavior of a molecule, but we simply cannot simulate that. We don't have the compute power to simulate even a medium-sized molecule like caffeine, for example. And this is because of quantum effects. So in the 1980s, the idea came about that we should use a new kind of computer based on these quantum effects to simulate nature at the molecular level. So what are these quantum effects that are so difficult to compute? I'll go through some of them that are the most important. The first is the uncertainty principle, which means that if you have a quantum system and you learn a property about it, you lose all your knowledge about other properties. And this means you need to deal with uncertainty, so we deal with probabilities. But it gets a little bit worse because we use negative probabilities. Actually, they are complex probabilities, but negative is weird enough for us now. And that means that you can have a positive probability of something happening and then a negative probability for that same thing happening, and they will cancel each other out and give 0 probability for that event. And this is not something we see in our day-to-day lives. And also, the third thing that's weird a little bit is the measurement update. So there's a probability for every value for a property, but once you measure that property, you get a value out, and the probability for that value you measured is 100%. All others go to 0. Now, how do we use these effects to build a machine and do math, do computation with it? We use the qubit, which is the simplest system that has these properties. And this is analogous to the classical bit that can have 0 or 1. The qubit has the probability of being in the 0 state or the 1 state. Those brackets that you see at the top around 0 and 1 are just a way of us to show that we are talking about quantum states. So the qubit has these probabilities, and they can be negative or complex. And we can measure the qubit. We have, in this case that I'm showing, we have a large probability to measure it as a 0, and then it updates to be 100% sure in the 0 state, and a lesser probability, just because the red segment is shorter than the blue segment on the left, we have a probability to measure it as 1, but in those cases, the qubit will update to 1. So because we deal with this kind of probabilities, we must do a lot of measurements to find out the exact state of the qubit was in initially before the measurement. And it's very important to note that qubits combine exponentially. 2 qubits hold 4 probabilities, 3 qubits 8 probabilities. With 30 qubits, if you want to simulate them, you will have to hold a state that's 8 gigabytes and would probably fit on a laptop. But with around 80 qubits, we go to the order of the number of atoms in the universe. So it's pretty difficult to simulate a quantum computer. That's why we need these machines. The idea of or the goal of a quantum algorithm is to have the probabilities for the state that represents the true answer for your problem interfere constructively and build up. And all the other states that represent the wrong answer, they should interfere destructively and go to 0. It's really difficult to build something like that. And we do operations on qubits using quantum gates. This is analogous to the Boolean gates of Boolean algebra, like we have the AND gate, the NOT gate. We have quantum gates. Most of them are analogous to the classical ones, but we also have some that are not analogous. I'll only show 2. One of them is the X gate, which is analogous to the NOT gate in the classical Boolean logic. This takes a qubit in state 0 to state 1, and the qubit in state 1 to state 0. The second one I need to show is the measurement gate, and this just tells the quantum computer, measure this qubit, give us the results, and after it, the qubit will be updated for the measurement principle. A typical quantum algorithm would be encoded in a quantum circuit using all these gates, and it needs to start in 0. The promise of the quantum computer is that qubits start in 0. We perform operations during quantum gates, and at the end, we measure all the qubits to get our results out. And now the question comes, how do we make such qubits? Like a bit is an abstraction. It can be a transistor or a capacitor or something else. Photons can be made in multiple ways, multiple systems with quantum behavior. What I want to touch on is the last one, the superconducting circuits. So these are all technologies that compete against each other, and we don't know which one's going to win in the long term. But one of the most popular and the ones we used mostly was superconducting circuits. And these are electrical circuits that are cooled to really low temperatures, and they have energy levels which exhibit quantum properties. So engineers isolate the bottom 2 energy levels to act as the qubit. But keep in mind that they have higher level energy states because it will be important later. And in this space, the market is growing. Qubit sizes, QPU, which is the chip size, are growing in number of qubits, and they're getting better. We have big players like IBM and Google, but we also have specialized players like IonQ, Quantinuum, and Rigetti. And now we need to know what are the applications of quantum computers. We first touched on the chemistry and physics where the idea came from, but most of you know about cryptography, where it can break RSA. There's optimization, complex simulations, and quantum machine learning. So how do we use now a quantum computer? These are very sensitive and expensive machines. You won't be having any one on your desk anytime soon. What we do is there's a provider that hosts it in the cloud, and you have API access. And you would encode your simulation or your program in a quantum circuit. You would optimize that for the backend. This is called transpilation. You send that to the cloud where it queues. Queue times can be really long, like hours. And after it finishes, after it gets to the top of the queue, it executes, and you can get your results. The question is, how do I build my quantum circuits? There are some meta-programming languages. Most of them, but not all, are built on top of Python, and Qiskit is the most used one, the most popular, and we mostly use that. Lastly, why would anyone attack a quantum computer? What would they want to do with it? So, like any expensive system that can have good results, somebody might want to disrupt their operation, like do a denial of service attack. They might want to disrupt the usage or the operations of a specific user, target some specific user. They might want to steal the circuits. If you know what's being researched, stealing a circuit would give you insight and allow you to reverse engineer research. More sophisticated attack would want to steal the results. These are just numbers by themselves, but if you know the circuit and what's being simulated, this can be really useful, stealing the results. And lastly, somebody might just want to do their own computation using somebody else's credits. And now I'll let Adrian talk us through the threat models and attack vectors.
So now let's see what we did in this investigation regarding quantum computers and cybersecurity. We tried to discover all the possible threat models and attack vectors. But during our investigation, we started from the point that, quantum computers are seen as possible as weapons. We noted the fact that they could be possible targets. Another aspect is that quantum computers coexist with classical computers. And maybe for many years from now, they will be used together. Specifically, quantum computers could be accessed and used using classical computers. Because of that, we actually know that an attacker could use either quantum computers or classical computers, or just a combination of the two, to target either quantum computing resources or classical quantum computer resources. And starting from those observations, we tried to classify all the possible threat models and attack vectors, resulting in a classification like that. You can note on the left side the weapons, which are, as I've mentioned before, quantum and classical. At the top side, the targets, which again are classical and quantum. And we have this all possibilities, classical on classical, which for us means that an attacker uses classical computing resources to attack the classical computing infrastructure, which provides access to the quantum computers. In particular, for us today, this means, for instance, quantum end user computers and the quantum computer and the cloud services which are used to provide access to the quantum computers. Similarly, we have classical on quantum, where an attacker could use classical computing resources to target a quantum computer. And at the top level, we have quantum weapons, quantum computers to attack classical resources. Here is, for instance, the attack against classical cryptography, or quantum over quantum. And along our investigation, we developed some proof of concept attacks, specifically in the category of classical on classical and quantum on quantum, respectively. We were restricted, obviously, by different terms of services, terms of use. That's why we focused our investigation on the end user computer, specifically on the SDK the user is using, or all those aspects, and also against the quantum computers, but just running programs as regular authenticated user using documented public API, things like that. So let's see our first kind of attack in the category of classical on classical. But as I told you, specifically for us, is about the infrastructure, the classical computing infrastructure providing access to the quantum computers. We use Qiskit SDK just because it's very popular. And we based our investigation on a particular threat model among maybe the many others, but we try to simplify a little bit our investigation. So what we consider is that the attacker has kind of control on the end user computer, being able to run malicious code at the current user privileges, and consequently being able to tamper with the end user processes, data. In particular, those data could be the files, some files, or the SDK files themselves, the quantum SDK files. Or alternatively, we could consider the case where the attacker has no control, direct control on the end user computer, but it succeeds corrupting the SDK in some way. Maybe the end user downloads the SDK from untrusted sources, or just because the attacker succeeds corrupting the SDK via a supply chain attack. We used the Qiskit SDK, as I've mentioned before. Also, our investigation focused on the quantum platform provided by IBM and IonQ, but we are pretty sure that it's not our findings are not specific to just to this SDK and quantum providers. Maybe they are more general. And also because we consider that particular threat model of the attacker having control on the end user computer, you'll see that doesn't make our attacks irrelevant. But even if they do not show directly exploitable vulnerabilities, they still show some weaknesses, which in some particular conditions could translate in vulnerabilities. The first attack that we developed targeted the API tokens used to authenticate the end user quantum program with the cloud services. Which were the problems, the issues we identified regarding that tokens? First was that those tokens were generated in clear text, and they are used exactly like that without any additional verification. Even worse, those tokens could be placed directly in the code. Okay, we checked that for IBM and IonQ. There are some very small differences, but the idea is the same. Let's focus on the first problem. So the token is allowed to be stored in the code. Okay, that leads to the classical problem of having secrets hard-coded. Once the code goes public, so does the secret. So this is not good for those API tokens as well. The Qiskit SDK allows the token to be saved on the disk, for instance, in a file, in particular for the IBM provider. That is a JSON file which is stored in a well-known location. It's somewhere in the home user directory. Its structure is, again, well-known. The problem is that the token is stored here also in the clear text. Alternatively, the SDK allows the tokens to be configured to be stored in environment variables. Again, that's the same for IBM and IonQ. But once the attacker gets access to the end user computer, it's very easy for it to read the environment of a process, to reach the files where the token is stored, and just steal it from there. Once the token was stolen in our investigation, it was used as it was without additional checking, as I told before, and that gives the attacker the possibility to authenticate on behalf of the victim, to run programs on behalf of the victim, consuming the victim's quantum credits, or see the history of the circuits the victim run or their results. Which are the recommendations in this regarding this issue? Obviously, firstly, not to store the API token in the code itself. Secondly, try to keep it encrypted, decrypt it only when in used, and if possible, enable multiple factor authentication regarding the usage of that token. The other attack that we investigated targeted the quantum circuits. We wanted to see if it's possible for the attacker to tamper with the victim's quantum circuits and hide that from the victim themselves. If we saw that if the SDK get corrupted, and as I told you, that could be obtained by an attacker via a supply chain attack, or just because being able to run code on the end user computer and corrupting the SDK. So once the SDK is corrupted, the attacker is able to tamper with the victim circuits, leaking them if needed, or changing them or inserting malicious circuits alongside the victim's ones and running them on the quantum computer. We derived a synthetic attack on that. We tried to make hard the job of the attacker, imagining that he has no idea where the SDK file system location is. Okay, in order to identify that location, we monitor all the processes in the system, trying to filter only those running the Python interpreter, just because the Qiskit is based on Python. Once we identify those processes, we read their environment, trying to identify only those using the Qiskit packages. And once we identify those processes and implicitly the location of the Qiskit SDK, we changed it. And we try to change the SDK to corrupt it such that to interfere with the victim circuits after them being transpiled. Transpilation, as Sorin said before, means that what the user designed and looks in some way is transformed in something which is specific to the quantum computer the circuit is to be run, and is optimized for that quantum computers also. It's just kind of a compiler. Okay, we looked at the circuits after the transpilation phase, and luckily for us, they were translated in an open standard language, the QASM, is quantum assembly, and we were able to tamper with those circuits and to inject malicious ones. And we do that and also manipulate the SDK to hide all those malicious operations from the victim themselves. What to do regarding that issue? The first thing, which is direct responsibility of the end user, is not to download SDKs from untrusted sources or just check the integrity of those taken from trusted sources. Maybe even more than that, we could try to isolate the SDK and all the processes using the SDKs from possible interferences, like, for instance, configuring a security solution to monitor for the SDK's files integrity, or to trying to run those processes inside isolated, trusted environment, like, for instance, Intel SGX enclaves. Good. That was about trying to see issues regarding the classical infrastructure giving us access to the quantum computers. Now, let's move on and switch back to Sorin to see even more interesting attacks regarding the quantum computers themselves.
Yeah, so how do you go attacking a quantum computer with quantum elements or quantum phenomena? This is a totally new topic. So we first approached it to see if anyone had thought about this. So we searched for articles, and we found a handful of articles, but to our disappointment, they were all handling a specific scenario which is not in use today. The scenario is that in order to shorten those queues, you would actually build up quantum circuits, send them more than one quantum circuit to run on the quantum chip at the same time, if the chip is large enough and the circuits are small enough. And this would mean that on the quantum chip, there's more than one user's circuit executing at that time, and this opens up a can of worms in terms of security. But we wanted something else. We wanted something that can be done today, at least in principle, and we focused on errors. We know that quantum computers have high errors on qubit, on gate fidelities, measurement errors, and we focused on the qubit reset operation. Why is that? Because if people queue up their jobs to run on the quantum computer, and the reset operation between these jobs is not good enough, then information can leak from one user to another, and all an attacker has to do is measure the qubits and get the results that were read by the previous user. So imagine you run a pharmaceutical company, and there's this new promising molecule that would be ideal for the treatment in a new disease, and you assemble a team of scientists, of engineers, of physicists, all highly trained, highly paid. They come up with a quantum algorithm, and then your competition runs a job after you. If he knows a little bit about what you're doing, he just reads the circuits and gets your result, and all your competitive advantage is down the drain. So is this possible, we asked? We started on a small scale of 7 qubits. We needed to take into account the limitation of the provider, which was IBM in our case. We use a backend called IBM Osaka, which is 127 qubit large, and we just use the 7 qubits because 7 qubits would mean that it would hold 128 patterns of zeros and ones. And we would need to get statistics on those because they are probabilistic, and we would need at least 100 shots per each pattern in order to differentiate between them. So 19,000 shots was what we chose as our number for running each circuit. So we designed an experiment where we had a victim and an attacker. And for the victim, we would prepare a random sequence of zeros and ones, and then we would measure that sequence. And then the attacker would just need to measure all the qubits and see if he can get out what the victim had prepared. So for the victim, we wanted to simulate this. This is just to simulate somebody running a complex algorithm and then ending with a measurement to get the results. So our attack model went like this, take a 7-bit log pattern of ones and zeros, let's say 1, 1, 1, 0, 1, 1, 1. Create a circuit for the victim that prepares and measures, create a circuit for the attacker that just measures the qubits, bundle them up in a single job, and send that for execution 19,000 times, and then interpret the results. So what do we expect from the results? We want to get the statistics of what the victim measured and get statistics of what the attacker measured, and then compare them to see if the attacker could indeed replicate what the victim had before. And our results, well, they were not very good. We were a little bit naive, and because of errors and basically measurement errors, we didn't get good results. So we couldn't reliably show that the attacker could recognize the pattern. So we needed to deal with these errors, especially with the measurement errors. So the most important error is the probability of measuring 1 if the qubit is in state 0. And luckily, the vendor, IBM, reports this error as a property of their system. So we thought that in the ideal case, when there is no information leak, I mean, the reset is perfect, or actually there is no information leak from the victim, then the attacker would only measure a 1 because of this error. So we tried to design an experiment to find this baseline. So we used the same setup as before, but now we have the victim just prepare the all 0 pattern. This means no information on the chip. Now the attacker measures, and we know what the attacker measures, and compute the probability of the attacker measuring a 1. And we expect this to be exactly or close to the probability of measuring 1 if the qubit is in state 0, as reported by the vendor, IBM. So these were our results for the baseline experiment. And the orange bars are what IBM reports as the probability of, so the measurement error as the probability of measuring 1 when the qubit is in 0. And the blue X's are what the attacker measured in our experiment. So they pretty much line up, of course, accounting for statistical error. So this tells us two things. One, that IBM is right. They report accurate measurement errors. And we are right, as the baseline indicates, because our baseline experiments matches with IBM. So now that we have this baseline, we say that if there is any information to be leaked, then on the attacker side, we should see an increased probability of measuring a 1. So we designed another experiment, which is the excited state experiment, where we use the same setup, but now the victim prepares the all 1 pattern. So we know note what the attacker measures, and we expect to see a higher probability of measuring a 1 on the attacker side. And these are our results. So let me explain a little bit. All that bundling up of circuits and executing them 19,000 times, we did all that 32 times, 16 times for the case when the victim prepared 0, and those are the blue marks on the graphs for each qubit, and another 16 times for when the victim prepared the 1. These are all attacker measurements, by the way. So we can clearly see that the red axes, which represent the case where the victim prepared the 1, are mostly above the blue axes, which means there is an information leak because the attacker's probability of measuring a 1 increased when the victim had a 1 on the qubit. So we can clearly see that on qubit 5 and qubit 6, where there's a gap there, but less so on qubit 0 and qubit 4, where there's a lot of overlap, which means that the reset operation on those qubits is a lot better. So now we try to build a model on that, which is just a threshold on the attacker side. So this characterizes the backend, and we have on each qubit, we have a threshold. The attacker has a threshold, and he gets statistics, and when the probability of measuring a 1 is lower than the threshold, the attacker assumes that the victim had a 0 on that qubit, and when the probability is higher, then the attacker assumes the victim had a 1 on that qubit. And what we did is repeat the initial experiment with the random patterns, but this time we used this model to interpret the results. Yeah, we checked if we could recover the victim's patterns this way. And we used a bunch of random patterns, and we could compute an accuracy for our model. And we can see that for qubit 5 and qubit 6, where there's a gap between the cases when the victim prepares 0 versus 1, our accuracy is really good. Like for qubit 6, because there's a large gap there, we have a 100% accuracy. For qubit 5, it's lower, but still good. Qubit 0 and qubit 4, they are not so good. I should mention here that the worst the model can do is 50%, because that's just a random guess. So for qubit 0, the model didn't do so well. Anyway, but this is, I would say, a pretty good result. This is something that clearly needs addressing from the vendor and from the users also. But Adrian here, which is our cybersecurity expert, took one look at this and said, there's a better attack hidden here, a way better attack. So let's switch around the victim and the user and the attacker. And now the attacker goes first. And he can influence, if information leaks from one job to another, then the attacker can influence the jobs that run after him. So remember that all the quantum circuits need to start at 0 in order for the computation to work well. If the attacker prepares all 1 state, then there's a small probability that the qubits from the next circuit will be affected and they won't be 0 anymore. So this clearly affects the next circuit, and it's can give negative results. So in this case, the attacker can prepare the all 1 state, just measures, and then the victim that comes after is not sure whether they start in the 1 or 0 position. So remember the team that you assembled to build and simulate that molecule, the scientists. Now your competition they have their own team, their own quantum computer. They don't want to steal your results anymore. All they want to do is delay you. And by running circuits before you and leaving them in the one state, they can delay you. And this is just from our initial results. We didn't have to do anything else. We just interpret what we had before. But it turns out there's a more powerful attack here. So remember that superconducting qubits have higher energy levels, and there's a quantum programming language that allows us to excite the qubit to those higher energy levels. And if we do that, so if the attacker leaves the qubit not in state 1, but in a higher energy level, then the effect is much more powerful. Overlapped on our previous results, we have the green marks, which are all around 50% on all the qubits. This means that the victim who runs after the attacker had raised the qubit to the second excited state has no confidence whether the qubits start in 0 or start in 1. So I would say this is a really powerful attack. And now the question comes, does this apply for these 7 qubits, or is it a problem for the entire chip? So we ran it on the entire 127 qubits for IBM Osaka, and we see that this is a problem across the chip. And then we think, okay, is this a problem for the technology? Do other chips have the same behavior? So we took another chip from IBM, which is IBM Sherbrooke, and also displays the same behavior. The probabilities are around 50% of the next circuit starting in 1. It is important to note and not to overstate what we discovered here. There are some limitations. So in our experiments, we assumed that the attacker runs their circuit after each execution of the victim's circuit, which is not the case if you just run your job in the queue, like on a quantum device in the cloud, because then you would only get one statistic, one data point. What we did is we interleaved the attacker and the victim circuits on every shot. But if the attacker is determined enough, they can, and you repeat your experiments, they can also get multiple data points. There's another assumption that we did here is that the reset between circuits on the same job is the same as the reset between jobs. And we reached up to IBM to see if that's the case. And they said, no, that's not the case, but they were really vague. They didn't give us a statistic or a length of the reset, and we couldn't test that. So we take that as at face value, but we would love to test that. Currently, they deny our request, but maybe in the future we can test it. So there's a lot more to discover. We only scratched the surface. This is just one scenario we looked at. There are other chips, other technologies that we want to look at. There's the IonQ ions that we know are also reset between circuits. How do they do? We don't know. We need more people to get involved. We need you to start thinking about, okay, these quantum computers are coming. They're going to be useful. They're going to be used. We need to protect them. So this is up to you. And if you want to know more, we'll be around here. Write to us on email. Get our white paper using the QR code. And let's talk after. Thank you.